Welcome. Today I'm going to show you how to do this truss calculation here. First step is to figure out if it's statically determinate, and the way that I do that is to use this very simple formula: 2j equals m plus r. J stands for the number of joints in your truss, m stands for the number of members in your truss, and r stands for the number of reaction forces. Those reaction forces are specific to the connections. So if you have a pinned connection, it has both a horizontal and a vertical, so that's 2. And if you have just a roller, that's 1. It's usually just a vertical connection. So I'm going to go ahead and do my calculations and my counting, and you'll see that 6 equals 6. So yes, unfortunately, we have to do the math in this. If you got 7 equals 6 or 6 equals 4 or something like that, the truss won't work anyway. It won't be stable, and so you shouldn't have to worry about it. Next step is to use trig to figure out what the angles are. I don't need to worry necessarily about the lengths of the members unless you have a specific question about that. And so what I'm going to do is just use the sine, cosine, tangent, and inverse sine, inverse cosine, and inverse tangent, and later on I'll use the Pythagorean theorem to be able to figure out what those angles are. So I'm going to go ahead and use the inverse tangent of 4 feet over 8 feet to figure out the angle at C, at point C right there. And you're going to see that that is 26.6 degrees. Now, I'm going to use the inverse tangent again of 8 over 4 this time to figure out what the angle at B is. But being honest, I don't really need to do it that way, because if you remember correctly, the sum of all the angles in a triangle always add up to 180 degrees. And so I could have just used the fact that A has a 90-degree angle and C has a 26.6 degree angle to figure out what the other angle should be. So you can do whichever one you want. Hopefully that makes sense. All right, we're on to step 3. And step 3 has to do with moments, which are the force applied at a certain distance from a pivot point. And this idea that for things that are not changing their rotation, they should be in rotational equilibrium. So we pick a pivot point, and the pivot point we almost always pick is the pinned connection. And then we try to figure out which moments are occurring around that pinned connection. And the moments that you see here are one clockwise moment of 400, because it's 50 times 8, and another counterclockwise moment that we're not really sure about. But we can go ahead and solve, and in the process we realize that the force that's acting on the roller must be 100-pound force upward. Okay, on to step 4. And in step 4 we use translational equilibrium, which states that all the forces in the vertical dimension must cancel and all the horizontal forces must cancel. And so we're going to start with verticals. We have a 200 down force and a 100 up force that we know about, and then one unknown. And that unknown is at A sub y. So what does that one unknown have to be? Well, by using some very simple algebra, we can calculate that it must be a 100-pound force up. And so that's what you're going to see as we go through that equation. So 100-pound force up is A sub y. Then we can do the same thing with the horizontals. Now the only one we know is a right force of 50 pounds from the wind, and then we have this unknown at A sub x. And so you can imagine that, of course, that's going to be 50 pounds to the left. And so you can see negative means left in this case. So we have to redraw the arrow to make sure that we understand that it's to the left. So now we're going to go ahead and transition to our last step, which is the method of joints. To start this process, we're going to go ahead and take a look at each individual joint by itself, which is where it gets its name. So we're going to rewrite each of the joints separately on the page. A dot represents the joints, arrows represent the forces we know, and lines represent the forces we don't know. Starting at joint A, you can see that a 100 up force must be canceled by a 100 down force, and a 50 left force must be canceled by a 50 right force. It's important to remember, though, that that down force actually means compression, and so we trace that member up to the top at joint C and make sure that there's a 100-pound compression force at the top. We make sure that the 50 pounds of tension on joint A is also traced over to joint B, where that same member applies a 50-pound force of tension. Finally, we can go ahead and go up to joint C, in which we see that there's a 200 down and a 100 up force already, so that angled force must supply a 100 up force. It also must supply a 50 left force to cancel the 50 right force. using the Pythagorean theorem, we can calculate the angled member force of 112 pounds. That is pushing into the joint, so it's compression, so it means we need to trace that back down to joint B, in which case that angled member still has a 112 pound force of compression. Hopefully that makes sense.